This is a production of Cornell University.
All right, so welcome everyone. Thank you, Jason, for the introduction, and thank you for having me. So, like Jason said, I will start my talk with a little introduction about who I am. So I did a bachelor's and a master's in Wageningen in the Netherlands in an environmental sciences program. So the bachelor was called Soil, Water, Atmosphere, and as that I like to think of myself as sort of a systems thinker. So I have a little bit of everything. And we used physics, mathematics, biology, chemistry to understand the world around us. After my bachelor, I decided that I like the air the best. So I specialized in meteorology. And from there, I stayed in the Netherlands, but moved to a different university, the other side of the country, the TU Delft, where I'm now at the civil engineering department in my final year of my PhD. My PhD is about local climate related to frost issues. So there are a couple of things that I focus on, and I will talk you through these topics today. So the first one is my favorite frost mitigation measure, which are the big wind machines. I've seen a couple of them around here. They're very sparse in the Netherlands, actually, but apparently they're more common in America and also in Australia and New Zealand. That will zoom in to the micro scale, to the scale of one branch, and that will be probably a bit more related to your field. And finally, we take that systems thinking approach and we'll very quickly also touch the topic of cover crops. But before we start, I will just want to set the stage, and this is probably well known to you, but let's just go through it very quickly. So when I'm talking about frost, even though I came here in winter, I'm actually interested in spring frost. As during the growing season of the plant, the cold hardiness or the resistance of the plant to withstand cold temperatures is going down. So the critical temperature, the temperature range in which we start to see damage, that one is approaching 0 degrees Celsius. So if in early February we have a frost of -5 degrees Celsius, most of the buds are still in the dormant stage, and that's actually fine. But if we have that same frost, if we have that late in the season, say April, then we'll see, well, more than 90% damage. And with climate change, this is becoming more and more of an issue. Not per se because we have more frost or because the frosts are more severe, as it seems now, but because that growing season is moving forward with warming temperatures. So earlier in the season, the plants become more sensitive to the same frost events. Well, we have seen a couple of examples of that in the past years, and it's kind of mean, but I'm kind of glad that that happens, because people ask me a lot about my PhD, like, is this actually an issue? And if it didn't happen, what would I be researching? But this is an event from France just after COVID, where about 80% of the vineyards were damaged. And that was pretty bad in this time because it was just after COVID, so they already were going to a rough patch. Also, another wine example from up here. This is last year, May, around the time that I reached out to Jason, not knowing that you actually just had this bad of frost. But well, it worked in my advantage because here I am now talking to you about frost issue and how to mitigate damage. Let's jump into the meteorology. So, very simple question. Why is it cold? When we look at frost, there's actually two types of frost. So not every event is the same. The first one is the one that you probably think about when you think about frost, and that's an advective frost. So what's happening in this case is that we have some advection, cold air from other regions being blown into your orchards. So as you can see, it's cold at all heights. And because the air is being blown in, this means that we do have wind. Important fact. This can happen during the day, it can happen during the night. It mostly happens during winter because we need to have a colder region for that air to being blown in to your region. But this is not the one that we're going to focus on during spring, because what happens during spring is that the daytime temperatures are already rising, which means that our ground is warm during the day because it's warmed by the solar radiation. However, during the night, we do not have that warm solar radiation warming it up. So our surface will cool. And as a result of that, that cold surface will cool the air. So that's something to think about, and that I chatted about with Jason a lot. It's not the air cooling the surface or the plants, it's the surface that's cooling the air. So now we have all our cold air exactly where we don't want it, just between the trees. And above that, it's warm. This is what we're talking about when we're talking about inversions. That strong temperature jump just above the trees. So those are the two types of frost. Now, there are a couple of things that farmers can do about that. And the first thing is to think ahead. Don't have your orchard in the lowest spot in the field because we will have some cold pooling, all the cold air draining to that area. So choose smartly. If you are in that cold area, what we see, and this happens, for example, in Spain, I believe, that they're blocking off part of the orchard, so to redirect the cold flow and so this stays warm. That's managing cold air drainage. Another thing that you probably know more about than I do is nutritional management. And finally, there's also soil covers, because as we saw, that cold is coming from the ground. So what happens when we change our cover crop, and that's that cooling situation going on there? So that's a question that I took up here to Geneva. And this is a little trial experiment that Jason and I did, where we had in the apple orchards over there, we had a patch that has some cover crop. It's some wheat that we pulled out from a nearby field because it was winter. We could not just plant something in 3 months and hope it would grow. So this is our cover crop field. And we had another one with bare soil. And what we did was we built a little temperature profile measurement setup. So all the white boxes that you see, they measure temperature. And we could compare these two sites, which were very close to each other. Now, this is a little bit of what we saw. So we measured for over a month. And what I did, I like to look at bulks of averages. So we grouped them by warm and sunny days, cold and sunny days, warm and shady days, and cold and shady days. And all the gray lines are individual days. What you don't have here a lot is warm and shady days. Warm and sunny we had quite a lot, so I came for the cold winter weather. That didn't really happen. What do we see? We see a diurnal cycle. So during the day, we see a huge difference between cover and no cover crop. So this is the daily average, or this is the average of the one thermocouple that's inside the cover crop. And we see that, well, if it's warm and the sun is out inside the cover crop, it will be warmer. Now this is interesting because this is exactly the height where we have the grafting, the graft unit. So it should more or less protect our graft unit during winter. Now the thing is, something to think about, so we don't want to protect it when it's actually warm and sunny, even though it's 5 degrees warmer. We want to protect it when it's cold, when there is no sun, and then we don't see any difference. So this warming has to do with the sun warming it up, but if we don't have that during the night, it will not make much of a difference. Now there are some more active measures to protect your crop. So these are, with active, we mean that the farmers go actively out into the field and they apply them at the moment that they need it, instead of in advance. This one is very popular in the Netherlands because we have a lot of water. It's sprinkling. You spray a layer of water from up top onto your buds, and freezing water has a temperature of 0. So as long as we have water that freezes on, that will protect your buds because it will take them to a temperature of 0, which is okay. But it requires a lot of water. You can also, it's like 2 thunderstorms coming over in one night. So it's bad for your soil. It's not the most sustainable measure. And even in the Netherlands, we're running out of water. So this one is, we need alternatives. This one you also saw on the first slide. This is the hot pots. In France, they can only use these for some quality reasoning with the wine that I don't think makes any sense, but they can only use the hot pots. And you can also for cherry trees, this is the only option we have because the ice is too heavy for the tree. So they need an alternative. I don't know if any of you ever worked with them. I joined a farmer or a grower into the field one day, and they're just so cumbersome because they keep falling over. And then they go out, and you have to go back into the field and light them again. It's a terror. Also, they're not very sustainable because they create a lot of smoke, and that's just bad for the air quality. So again, a need for an alternative. There's the alternative, my favorite one, the wind machine. So we're going to focus on that one a little bit more now. Now, something I want you to realize, it's turning. It turns in two directions. So it's of course turning around like a normal wind turbine does. It's a ventilator, so it generates wind. It's not turning because of the wind, but it makes wind itself. But it also has to protect the entire field. So that's why it's rotating around its own axis. I used to be here and pretend I'm a wind machine, but I now have this little video to show it to you. Because I like to talk about wind machines. So the thing that I did together with a colleague of mine was we were wondering, how does the field actually warm when we have a wind machine? And can we model that? Can we measure it? So we wanted to create images like this. Spoiler alert, we succeeded. And we did that using this measurement technique that's called the distributed temperature sensing. So it's a pretty fancy technique. It's also quite expensive. But what you do is we have this computer and a very long cable. And we send a laser signal through the cable. Now, the backscatter of that laser depends on the temperature of the cable. So along the cable, we actually know the temperature. So you can just, we get like 9 kilometers of point measurements from that cable, from that one measurement device. And it also has a pretty high temporal resolution. So we get every 10 seconds, more or less, we get a measurement. So a lot of data. We took this device close to home for me, actually. So this is home, the southwestern part of the Netherlands, close to the coast. And we took it into a pear orchard over there, where we had the cable going back and forth and back and forth and under the ground and back and forth for 9 kilometers. So this took us with 6 people 3 days to set it up. And it's terror to the farmer because you all of a sudden have this super sensitive cable hanging in your orchard and you cannot do anything. So you can imagine the effort that went into this experiment in just digging it below each row so they could still drive their tractors over it and just connecting the cable to each tree. But we managed. So we covered this entire field, and we also had 3 masts. And with those masts, we actually had the cable going up and down. So we did not only have a horizontal grid, we also had some vertical profiles. I forgot to mention, but we actually did this at 2 heights. So it's even more. Now, if you look at the measurements that you can do with this is an example. So what we see here is the black line is a temperature profile that's measured without the wind machine on. So like we saw in the beginning when I explained the radiative frost, we have all the cold air near a canopy. I like to make plots this way. I should explain them a little bit. So we have height on the vertical axis and temperature on the horizontal axis. So what happens when we turn on the wind machine is that we sort of put a big mixer into our orchard and we start to mix that air. So the cold air that was down here is now being mixed up. And the warm air from here is being mixed down. So we get a more vertically homogeneous profile. Now it's cooling above our trees, but that's fine. We don't care about the air above our trees. We care about what happens at the tree level. So there we see on average a 3-degree temperature increase. Now I have a formula, but don't worry about it too much. What we use this formula for is to express the warming not in degrees, but actually in sort of efficiency. So we could compare amongst different nights. Now it looks quite complicated, but it's actually pretty simple. It's the warming that we actually have, the red arrow, compared to what we would have if we would have maximum warming and all the heat would be transported down. So it's just a percentage. Now, because we had the cables going back and forth through that field, we could make maps. And this is still image, but I will play it for you. So this is how we see the warming signal spread over the orchard. Here, this warm spot, that's our wind turbine. And you could just see the jet moving around. I find this so amazing that we could do that. It's like a model, but it's actually, we measured this. Really cool. Little self-promotion here. So if I average this signal over all these rotation cycles, which take 5 minutes, we'll see, well, this hotspot, like I pointed out, that's the engine heat, because it is running on diesel. So there's some room for improvement there. But what we also see is that the hottest spot is actually not directly in the middle of the field. And that's because the wind was coming from here. So there's no topography in this field. This is the Netherlands. It's as flat as a pancake. But we do have a very, very slight background wind just coming from that direction, and that's drifting our wind machine signal just up to the northwestern part. And I said in the beginning, I remember to say it, but for radiative frost, we don't have any wind, because if we would have wind, we would have mixing and we wouldn't have that cold layer near the ground. So here we do have a little bit of wind, but it's literally less than this. So if you're standing in that field and you're between the rows, you don't feel it. Now, why is it the effect that's strong? It's because we have this huge mass of air that's just pushing our signal or our heating away. Because it's slow, but it's huge. Jason compared it to a cruise ship or a ship hitting a bridge. You can imagine what happens. So let's see. Now, like I said, I'm at a technical university and we also like numbers, we like equations, and we like to model stuff. So we wanted to model this. And we used this technique called large eddy simulations, which basically means that we model the movement of all the air particles. So it's a very detailed technique that you can use to, well, actually resolve Navier-Stokes equations and really go back to the basics of what is happening here with the airflow. You can imagine that's quite computer power heavy. So what we did is we used an adaptive grid, which means, and that I also find this a cool technique that I wanted to introduce to you, is you actually have the highest resolution exactly where you need it. And the rest you can just use rougher grid cells. So here is our wind machine and our trees. And there we use this very fine grid because we have very large changes over short distances. And here up where we don't really care about and also not so much is happening, we can use that rougher grid. Now, I have to admit, I didn't do this work myself, but it's done by a colleague of mine. And I will just show you what the model looks like. So on the left side, you see the observations. On the right side, you see the simulation. And of course, it's not exactly the same. I mean, this one is quite stripy, but that's because we have the rows of the cables and we're just interpolating in between. So this looks more smooth. But if you think about it, that this is a model that includes a canopy, it includes topography, It includes a wind machine, and it just measures all those air particles moving around and warming by the canopy. I think it's incredible that we can do stuff like this. And it also gives you a lot of opportunity, because this is just our example case. But for a farmer, you could now test what would be the best location to put your wind machine. Because we saw that in the middle of the field is not per se the best location. And what happens then? We have topography, or we orientate our rows slightly different, or you have the machine under a different angle. You could test all these scenarios for each individual case, if you have enough money to run the computer every time. But in theory, it could be done. Now we will move to something that it's probably a little bit closer to your hearts. What about plants? Because so far we only talked about the air temperature, and who cares about the air temperature? It's the plant that's freezing, right? So can we translate from the air to the plant? This is a thermal image that I took during the measurement night. And what you can see here is, don't care about the exact temperatures, but do you see all the variation going on here? So we have different rows of trees. We have the ground. Some parts of the ground are colder, some parts are warmer. It's the difference between grass or mulch, and if we walk through it, so the grass is flat or not, that's all that variation on the ground. But also with the leaves, there's a lot of variation with height. If it's close to the tree, is it far out from the tree? So we took a couple of point measurements, just a sample, but see all the variation that's going on here. So for the point measurements, we used very small temperature sensors, and in this case, we were quite late in the season. So we had mainly leaves on the trees and some young fruits, but we pressed them against the leaves. So they're not thermocouples, you don't put them in there, we just press them against, because the energy exchange is more efficient between the leaf and the air than the other way, between the leaf and the thermocouple than between the thermocouple and the air. It takes the temperature of the leaf. So we measured leaf temperature and air temperature outside of the boundary layer, but just next to the leaves at 3 different heights, a couple of trees. And this is what it looks like. So again, my little animation. Now imagine you're a tree here, and we have the wind machine on, so it's rotating. It takes 5 minutes to make a full circle. So every 5 minutes, you feel this gust of warm air passing you. So these black peaks, they are the wind speed. So you see that going up. And the black peaks, they correspond to the gray peaks in the lower plot, which is the air temperature, because it's warmer air, because we're mixing, right? Now, if you look at the green line, and the green line is actually the plant temperature. And my one takeaway message, if you remember only one thing from this talk, is plant temperature is not the same as air temperature. And we can see that here. Because the farmers, they use to track the air temperature to see when does the machine need to go on. So in the gray zones, the machine is on, and it goes on here because the sensor that they used was set to 0 degrees. So machine goes on, first circle. Now, if we would have tracked the pen temperature here, this grower would have known he's too late, because that leaf temperature is already below 0 for about half an hour now. So that's enough to do some damage. What we can also see is over time, we're mixing. So the leaf temperature is actually closing in on the air temperature. The difference is becoming smaller. Well, we wanted to understand what is going on here. Why does this happen? So another model, this time my model. Here we're zooming into the scale of one branch. And we have a couple of processes going on here. The first one is turbulent warming. Second one, radiative cooling. We saw that one before. And finally, latent heat release, when there's actual freezing. So turbulent warming is what happens when we have warm air going over a cold plate. So if that plate would continue for infinity, they would get the same temperature, right? The plate would warm up and the air would cool down. Now, that depends on the temperature difference and on the speed of the air movement, how fast that is going. So first process, turbulent warming. Second one is radiative cooling, and that is what we saw at the ground. So that's the fact that we have a surface, a black body, that is emitting long-wave radiation. So it's cooling itself. Now, the efficiency with which that happens depends on the temperature of the surface, in this case the leaf, and it depends on where our leaf is inside our canopy. Because if it's nicely hidden between all the other leaves, they will all be emitting radiation. And it will sort of keep themselves at the same temperature because what one is emitting, the other one is receiving, and the other way around. It also depends on the cloudiness, because maybe you've noticed this, but if it's a clear night, it will tend to be cooler than when it's a cloudy night and cool down faster as well. That's because all that outgoing radiation will be reflected by clouds. So the system is keeping itself from cooling down too fast. Of course, leaves are they also face the ground partly. So also the temperature of the ground and the radiation that's emitted by that will warm and cool a leaf. So we basically have a very big radiation balance going on here. Third process, latent heat release. We didn't see that during our measurement night because we didn't have an actual frost. So I left that out of the model for now. So let's take a look at what we saw. This is the average, again averaging, of all the rotation cycles that we had with the reed machine. So the jet is passing us at time t is 0. So that's when we have the strongest wind and the highest temperatures. Everything before that, everything after that. Here the jet is approaching. So what we see is that the air temperature is going up. The leaf temperature is following, but it's a bit delayed because it's now, they used to be in equilibrium, but now our condition is changing because we're introducing warm air. So remember the two processes that I showed you before, turbulent warming, in this graph, the dashed line, and radiative cooling, the dotted line. Mind the axis, it's the negative axis. So the further down we are on the screen, the stronger the process. So what do we see? First, we see turbulent warming dominating. Why? Well, because our air temperature is going up. And the temperature difference between the air and the leaf is increasing. So strong turbulent warming. That happens until we reach a new equilibrium state. And it's again in balance with the radiative cooling. Now, at that moment, we have our jet passing by. So we have very strong winds. Again, strong turbulent warming. And it's that efficient that if you now take a close look, you will see that the air and the leaf temperature are almost the same. Which means that there is no turbulent warming anymore. So that goes to 0. And the dominating process is now the cooling, the radiative cooling. So the leaf will start to cool itself again. And we'll restore our difference and can restart our cycle. If you take a close look, you'll see that we end up slightly higher here than we started there. So after all these rotation cycles, our leaves are warming slowly, and that's why that difference became smaller over time. Now, the question that I had when I came here is, how does this change through the season? Because we only did one field experiment. And we only, like I said, we were very late in the season, partly because of COVID. So we only had leaves and some flowers that were already trying to change into fruits. So that's a question that I took to Jason. Also because I was interested in learning more about the plant physiology side. So we designed some experiments here with the freezer. So what we did was we collected some branches all at the same moment in the field. And we put them in the cooler, and then we pulled them from the cooler at different moments in time. So they were in different development stages at the same moment. Now what you see with the blue cables going on, those are the thermocouples. So these we inserted inside of the buds so we could track that over time. And then we set this whole setup, we took it and we put it into a freezer. Now this is not the same as a frost outside because we don't have any way for the radiation to escape, but it's an approximation of what happens. And this is what we saw when we looked at the thermocouples. So what you see is all these peaks. That's the freezing. That's the water outside of the cells that's freezing, and it releases heat because it wants to go to zero. I tried to find a link between the development stage that we're in and the moment that we saw the freezing. I was really hoping for some nice, clear conclusions on that, but also took some averages of the multiple experiments that we did, but it's a bit of a mess. So of course, there's a lot of biological variation going on there. There seemed to be a little temperature gradient inside the freezer, and there's just so many processes interacting. Plus, we took 3 different cultivars, which in hindsight maybe we shouldn't have done to make things clearer. But I like Jonnekolt because it's an apple that we have a lot in the Netherlands, and we make apple pie out of it. So it's one of my favorites. These 2 I never had heard of. They're very American. I like them though. Well, what we saw was that if you look at the green, so the green is the like from the tight cluster to shifting towards the pink stage. That one is all over the place. But what we do see is the buds, so the dormant buds or the like silver tip, green tip ones, they're ahead of the flowers. If we look at the time at which the temperature dropped below 0. Now, this is not the actual time because the buds, they sort of, I like to think of them as having a little winter coat on, so they protect themselves so they don't cool as fast. So if you would take here a normal time axis, what you would see is everything sort of freezes at the same time because the buds protect themselves from cooling down. But they are less resistant and they freeze earlier. Now I brought the thermal camera with me, and we took a little video of what was happening. And towards the end, pay close attention to the box, because what we will see here is the flower super cooling. So everything else seems to be frozen except for that flower. It's kind of cool to see. Oops. So, do you see them light up? That is the actual freezing exotherm that we see, because we're tracking temperature. I sped up the video, so it's about a minute. The 1 minute is 1 second. Here, that one just froze, and you can now see it sort of crumble. And this one is still getting cooler and cooler. Oop, there we go. Cool, right? So with that, I already set up, I'm going to be too fast because I'm already running out of slides. But if you want to see anything, or we can just do some questions in the end. I always like interacting with you. I'll go to my take-home messages. The first one being that not all frost events are the same. And that means that different events require different mitigation measures. So that's something for the farmers to think about, but also maybe for you, if you're working on cold temperatures, to just ask yourself, why is it cold? Is it windy? Is it cloudy? What's happening? Where are we in times of the seasons? The second one is that wind machines are great. They can protect your crop, but also think about where you place them, because just putting them in the middle of the field is not always best practice. And we've seen from our model simulations, actually, that sometimes instead of going the full circle, a half circle is even more efficient. And you may want to blow against the wind, because what you want to do is you want to generate turbulence. You just want to move your air, not per se move the warm air down. So models can help us understand in what best practices are. And finally, plant and air temperature are not the same. I cannot emphasize this enough. So don't just track the air temperature. See what's happening. Is it an open sky or is it cloudy? Is it windy? What kind of plant organ are we looking at? Is it one that is very thick like a bud? So is it keeping itself warm with its winter coat? Or is it something like a leaf that's very thin and it is losing a lot of radiation? Think about that next time you're tracking air temperature. With that, I want to tell you, this is not just me. Big thanks to the team at home. My advisor was van de Wiel, Marie-Claire de Veldhuis. Marie-Claire will be here next week if in the seminar. So stay tuned for that. And Martijn Vogelaar, who was kind enough to borrow his orchard to us and to have us all that cables going on and disrupt his work. All the students that helped us out with that. And big thanks to the Londo Lab, to Jason and Hannah. Hannah, I hope you're online. Thank you. And if you want to read a bit more about what we've done here, we've written 2 papers about that. One with me as first author, one with my colleague, Dai, as first author on the wind machine and the plant interaction with that. Thanks for your attention. Justine.
That was an excellent seminar. Thank you. You explained everything really well. What would your thoughts be on a wind machine at the vineyards along the lake here? So they're on a significant slope. So, and then even when they have radiative cooling, they still have some air mixing because of the lake effect.
Yeah.
So what are your thoughts on that? Are they useful or are they a waste of money?
Okay. So the question was, are the wind machines useful near the lakes when we have large slopes? And I think they are useful. However, what I would love to test is what happens if we would put them downhill and would have them just blow upwards. Because then we're blowing against the main direction of the flow that is flowing downhill. And we would be generating so much air mixing there. So I wonder, would that actually work? Or would we just reach a little bit up the hill and then it would stream down again? I don't know. I'm from the Netherlands. Slopes are not my expertise at all. Does that answer your question?
Yeah, thank you.
Okay. Yes.
Could you, in theory, like if you had a blank field that you were like, I'm gonna plant an orchard or a vineyard or whatever, could you use the wind machine to figure out like the best design, or does it only really work kind of after the fact to see where placement would be of a wind machine would be most helpful?
Oh, that's an interesting one. So the question is, thanks for that. The question is if I could in advance test what would be the best setup for my orchard if I already had my wind machine, right? I think you could do that because you have mobile wind machines that they use to move around the field. I'm not really into promoting brands over other brands, but I don't think they're as strong as the stationary ones. Don't let them hear me say that. But if you can only put your wind machine in one place, then I would say consider the main wind direction. And that's usually, well, it's the main wind direction. So usually the wind comes from the same direction if you have the dangerous conditions. And that you know in advance. Then you could say, okay, I will orient my rows according to that. But I don't know if you want to do that, because with the row orientation, I think the sun is more important in terms of how fast it grows than just that one frost event. And we also didn't see a really preferential flow along the rows according to across it. So you would not need to have an empty orchard to test your wind machine setup. Does that answer your question? Okay, great, thanks. You can go ahead.
In the anticipation of a radiational frost, how might you manage a cover crop? Would you cultivate? Would you mow it low? Would you want it to be high? I mean, since you mentioned that a lot of clothes from the ground up, so I'm trying to link it to cover crop management.
Thanks for that question. So the question is, ahead of a radiative frost, what would you do with your cover crop? And I love that you asked this, because this is the second project that I'm working on and I'm not presenting today. It's not straightforward, is the easy question. Because if we would have a bare soil, that would release more heat during the day, or it would catch more heat, and it would release more during the night. How, if you compare that to a grass site. However, I don't know what they do here, but in the Netherlands, bare soils are very, very unpractical. Because you cannot drive your machines over it. And here I've been in the field and it was all the mud, so I can imagine that it's not so great up here either. And if the thing that I started to look at is, okay, what if we just have grass? And we have tall grass compared to short grass. Would that make a difference? That's a tricky question. And we try to answer it in an open field. And there it did make a difference, but only up to like 1 meter height. Now, if I'm in an orchard, above my fruit will only start to grow above that 1 meter height. So I would say it doesn't matter that much if you have tall grass or short grass, as long as you don't have bare soil. However, what makes it interesting and complicated there is that we do have another canopy going on. We have our trees. So those trees, they capture the heat and they don't release it as fast as we have in our open field. And how well they do that changes throughout the season because we do or do not have leaves. So you're opening Pandora's box here. And I'm trying to look into it and understand it better, but I'm just like taking the first step. But I love your question. Thanks for that.
This doesn't grow as it cultivate in anticipation of a radiational frost.
Yeah.
Figuring that, yeah, muddy field, yes, but it's worth saving the crop. So.
Yeah, we have the same thing that I advise the growers to keep the cross short. I'm afraid it's just a waste of effort. Yeah, but it's been done that way for 50 years, so it's hard to convince people not to do it. Yeah.
So there's some devices out there that are being sold that will large fans sucking in air and then blowing that air up.
Yep.
And they put them in the low spots of the orchard or the vineyard, trying to create some airflow through the canopy, essentially.
Mm-hmm.
Have you looked into that, or do you have any thoughts on the practicality of that? It's
Yeah.
kind of a newer sort of tool, and don't have much experience.
Yeah, thank you for that question. So the question is, you have the fans that are sort of drawing in the air and then blowing it up. And if I have looked into that, I've read about them. I don't think they're as efficient as the machines that I showed you. And that's because it's not what's the process behind the machines is not the actual movement of the air that's causing the heating, it's the mixing. So that's why we can have that's why we see to quite a long distance, we still see the effect, even though you're like, or I'm so far away, the warm air can never reach that region. And I think that the machines that are drawing the air in and then blowing it up are not causing as much mixing as the ones that are covering our entire field. From what I've read, they're also less effective. But I would just love to have different machines and have the cables up there and have someone let me play around in their orchard. But that's my best guess so far. Yes, thanks for asking.
I want to see if there's anybody online.
Yeah.
Got a question here too.
Oh, yeah, I will answer that one. Yeah.
I guess I'm kind of curious how effective you think it would be to have more like static or passive fixtures throughout a field to kind of induce, I guess, turbulence from the wind that's kind of already blowing above the canopy and kind of draw it in for mixture. Or is it really necessary to have more of an active mixture process with something?
Okay, let me see if I catch your question correctly. So you're asking, would it be good to have machines that are using the wind that's above the canopy to sort of moving that into your canopy?
So like more like static fixtures, so not actively powered by anything, just like.
Oh, just sort of blocking your flow.
Yeah, like a wing on a car kind of thing.
I see, yeah. Well, the issue is that when we have our radiative frost, we barely have any wind. So I tried to explain this to Jason a couple of weeks ago, what happens when we have wind still nights and we go into a completely new unexplored field of meteorology, actually. when all of a sudden things are no longer driven by turbulence, but we have air moving up and down like waves. It's really cool stuff. But if we would try to generate turbulence during those conditions, we will actually not get any turbulence. So we'll not get any mixing because the flow is just too weak, even if we go up high. And if there is flow, there's not so much of a problem going on. And our trees themselves are already generating some turbulence because they are blocking our flow. Does that answer your question? Yeah. Okay, great. Oh, were there questions online?
There's nothing.
Okay, then I'll just continue with the room.
This is just say in there, if Geneva has any questions, send it to the chat.
Geneva, if you have any questions, just send it through the chat.
Do they come on with the microphone? I don't know what you guys do now.
They do it both ways.
Okay,
Okay.
speak up if you want to be heard.
Yes, go ahead.
Yeah, thank you for the excellent presentation. My question about the wind machine, since like it's mixing the air and there is no energy source, right? Just only mixing. How do you select the efficiency, or you know the efficiency of the wind machine compared to the low temperature? If you have like limit, as example, minus 10 Celsius, this will be efficient or not?
Okay, so the question is how efficient the machine is if there's actually not so much warm air above our canopy,
Yeah, exactly.
if the aeration is not so strong.
Many factors controlling the machine, right?
Yes, well, don't get me started on manufacturers and what they're trying to sell you, because the machine is very dependent on the inversion strength. If there's no warm air above the canopy and we'll just try to mix it, nothing happens. That is why it's not an effective measure during an effective frost, because we saw that that whole profile was cold, right? You can mix it, but we have no warmth. The only heat that's introduced into the system is by the engine, and that's quite a lot, but it's not a lot enough to cover your field. So there are some questions about what if we combine this method with the hot pots? And I think that would work because we're introducing heat, and one of the reasons the hot pots are not super efficient is because if you don't have any heat or any wind and you just have a warm source, it would just go up just between your trees and it will not actually warm your trees because hot air just rises. But if we combine that, then we might get some actual really efficient warming even during the nights that we don't have strong inversion. Now you would need to figure out a way to stabilize your hot pots because like I said, they fall over all the time. Okay, Andre?
Yeah, so my question is regarding the measurement of air temperature.
Yeah.
So when you turn the fan on, and is that possible for you to measure the air temperature using like thermal camera, like having a drone carrying a thermal camera and measure that above the chart?
So we had a drone during this experiment. It did not work out the way we hoped, so that's why I didn't show any of the images. But thermal cameras don't actually measure the air temperature. They just measure the temperature of surfaces. So you'll see the surface warm and cool, but you won't see the air. Now you can see the air if you have a very thin layer that directly takes the temperature of the air. So what we did together with a student was we had this very thin screen, kind of like this projector screen, but even thinner. And we put that in the middle of our orchard and had the thermal camera point at it. And you could see how the warmth spread over that screen. You can also imagine why this is not practical if you want to measure an entire orchard. Yeah, so that's the downside of thermal cameras. But they are very fun to play around with, and you can see how the trees warm and how they cool down again. And that's the actual thing that you're interested in, right? Not the air. Thank you for that question. Yes?
Can you give us an idea about how much one of these wind machines costs and how much area it would cover under ideal conditions? Like, how much would you pay per?
I get that question every time, and I don't dare to answer it because I once got the email from a manufacturer telling that I sold him short. So my answer would be, during this particular night, we had one orchard, which was 300 by 300 meters. And we saw the signal from the wind machine in the field next to it. So they were strong enough to cover about 1.5 field. But that was a particular night with a particular inversion strength, like we talked about during one of the questions, that it depends on the inversion strength. It depends on the background wind. So I've heard growers tell me, well, we have one of the machines and we saved, what was it, half a kilometer down, they were still seeing those effects. It could be during one particular night that you saw that. I don't dare to bite numbers to it because it depends on the brand and it depends on the night. Okay?
So, yeah, so I'm a grower and I need to make a decision here.
Yeah.
Yeah, how much, what's the range? You can just maybe give a range of costs
I would say, oh, the range of the costs.
for a wind machine. Yeah.
Okay, so the cost of one of these machines is 15K.
US.
Euros, 50K. Oh, no, actually dollars, US dollars. Yeah, because this is an American brand.
15 or 50?
1.5. It's expensive. So that's why you only see them in the bigger orchards. Yeah, I would recommend them.
And then there's the diesel costs.
Yeah, then there's the cost of operating it. And it sounds like if you're in a very crowded area, densely populated, it sounds like a helicopter is rising up. So, funny thing, these are actually not allowed in the Netherlands anymore because they're too loud. So for the sound pollution, so they're now working on a more quiet system, but that's less strong because the sound just it's linked to each other.
So you said that particular wind machine covered an area of 300 meters by 300 meters.
And it actually went out of that. Yeah, let me see.
On top of that, multiplied by 1.5. So that's almost 30 acres based on my calculation. 300 by 300.
Let me see if I can pull up the graph. Oh, it's all the way back.
I think I saw a range around 3 hectares. I thought you had highlighted.
Yeah, let's see. So
20 acres.
150 by 100, 250, and then it's going outside of this field even.
Very flat ground.
Very flat count.
This is 250, 300 roughly. Okay, so it's about 15 to 20 acres.
Yeah. The farmer that we went to had about 8 of these machines.
Okay.
Yes.
Is there a simple way of measuring an inversion? So if we have a farm and we want to know whether or not we frequently have an inversion, how would we go about doing that?
If you would go the simplest way, I would say have one thermometer inside of your canopy and one above, because there's quite some support structures.
How high up do we need to go?
At 9 meters, right?
Our maximum was at 9 meters. Above, if you look at it, so it's around 3 meter height. Then we see that inversion. So let's say 6 meters and you're safe.
6 meters.
So you would have one here, you would have one here, and you could get an estimate of your inversion strength. Yeah. Yes, you should do that in the spring. Yes.
Looking at frost control measures for a research farm.
Okay, that's
I
cool.
don't think that we get an inversion all too frequently,
Mm.
but we don't really know that, and so
Yeah, you don't need any high tech just for this.
we can simply we have lots of thermocouples. We can set this up.
Yeah, cool. Do that. Yes, go ahead.
What's the highest leaf temperature that you saw?
The highest leaf temperature that I saw during this experiment, 3 degrees, something like that. But if you're talking in terms of how quick the temperature rises with the wind machine, we had a temperature jump, an instant temperature jump of 8 Kelvin, from just -2 to +6. Yeah. If we're talking about during summer, we can go up to 50 degrees Celsius. Yeah. Just by solar radiation and no wind. Yes.
Because of the maximum warming effect,
Mm-hmm.
in the tree canopy is about 3 degrees Celsius.
Yeah.
Right? So this would suggest that if the lowest temperature for the night, let's say no wind, ideal conditions for inversion.
Mm-hmm.
So if the lowest temperature for the night drops to, let me see, 5 degrees,
Mhm.
5 or 6 degrees, you know, that would, this wind, this wind machine gonna bring the temperature up to 2 to 3 degrees minus 2 to 3 degrees Celsius. So that's typically the threshold level.
Yeah.
To blow. So for anything below that, even if you blow you use the wind machine.
Correct.
Yeah.
But if we have a very cold night, what we also see is that this inversion strength is actually,
Okay, it's bigger.
it gets bigger.
Uh,
It of course depends on each individual night, right? But we could have a stronger effect. This is just one case. That's also why I don't like having numbers, because it's different for every night. So we could go from -8 to 0 if it's just warm above here. That depends on how far we are in the season, actually. Yeah.
Thank you.
You're welcome.
So
Should I stop?
We're getting the hook out, so far out, we're
Thanks.
This has been a production of Cornell University, on the web at cornell.edu.